So first of all, I want to say a very big congratulations to our dance team. That was super awesome. First place and third. That's respectable, I would say. I don't know. Were you happy with the place? Good, awesome. And I also wanted to give a shout out to the show choir. I don't know about you guys, but I really, really enjoyed watching them on Friday during the pep assembly. So just wanted to say nice job to you all. I love seeing you guys in action in whatever capacity that is. So I just wanted to, say thanks for sharing all that you do. Today, our plan, we are going to start with a warm-up problem in just a moment. But before that, a couple of things. First of all, I'm going to give you your 3-1 and 3-2 quiz back. That was the quiz that you took last Wednesday with the ramps. And I had them, I just didn't get a chance to get them back to you. So I will get those back to you first thing. We're going to do some graph analysis and do some follow-up with that friction lab that we did on Friday. We will also work on some ranking tasks, and if we have time, then do some problem solving as well. The reason for that is that we have a little bit of a change in our schedule. I have not put it up on Canvas yet. I apologize. I will get that done hopefully today, but just so that you're aware of what we're doing. So that's our plan for Monday. Tuesday, we're going to do another little ramp friction combo lab activity. Wednesday is a check-in. It's listed on the calendar as a 3-3 and 3-4 check-in, but to be honest, it really is going to be a check-in of all of the Unit 3 because the 3-3 and 3-4 really are the math that go with drawing a free body diagram and an F-net equation. You can't really do the math without having set it up first. So on Wednesday, those problems will assess all of the standards, okay? Unit 3 review on Thursday, and then Friday we will take a test. The test will look similar to the quiz, but it will also have some qualitative problems on it as well, which is what we're going to practice today, okay? This is not a week of rest for us. In physics, we are going to hit it hard. We're going to go, so I need to make sure that you are with me and you're focused. I also want to let you know that we will start Unit 4 next week. We will be working all the way through the week. We are not taking Thursday and Friday off. In fact, we're going to work on a little project Thursday and Friday. If you know that you will be gone any of the days of next week, you need to let me know so that we can make a plan to plan ahead. Okay? Questions that you have for me before we get started? All right. So what I'm going to do real quick is to hand back your quizzes. I think most of you have taken it, but I don't have them all recorded yet. So if you've not yet taken the 3-1 and 3-2 quiz, it was on the ramps with the animals, then I'd ask you to go out in the hall real quick. Otherwise, I will get those to you. And the other thing that I would like to say is please, no phones out today. Please, no computers out today. I need your full and undivided attention in class. Today is 3 screenshots of graphs that I saw when I was grading, okay? And the 3 that I chose could have been a lot of different people's. Does that make sense? So it wasn't like I'm like, wow, like this one is really bad. And it wasn't that. These are common mistakes that I saw over and over and over. And I wrote the same comments over and over and over. And I want you to figure out, if you go ahead. Yeah. I want you to figure out what the mistakes are so that we can move forward in a positive way. So in your warm-up problem sheet for today, the topic is L3, which is the data analysis topic. And these are graph analysis is what I think I called it, okay? So I'm going to throw 3 different graphs up here for you to look at. We're going to do one at a time, okay? No names attached. It could be yours, but it doesn't matter whether it is or not because we're just learning together. So I want you to take a look at this graph, talk to your table mates, see if you can identify a problem or problems that exist in this graph. Have a conversation. I'm just going to give you a minute to chat, and then we'll discuss, okay? So go ahead and take a look. Problem, in your warm-up problem section, you can say example 1, and let's take a look, and we're going to write down some things that we observe in this graph that could have been done differently, could have been improved. And again, friends, the reason we're doing this is not to pick on anyone in particular at all, but it's to learn what to do and what not to do. Ben, what do you see? What's something that you want to add?
The x-axis, it goes from 200 to 500, but it's the same space as the first. So it should be like 200 to 400.
Yeah, that's the big thing. And friends, I wrote this over and over and over. Let's take a look at what Ben is talking about. So if we look at how this is going, it goes 1, 2, 3. Oh, thank you. 4, 5. So 6 tick marks goes to 200. So that means that 3 little lines would be 100, right? So this is 100, 200, 1, 2, 3. That would be 300. 1, 2, 3. This should really be what? 400. And then 1, 2, 3, 500, etc. Does that make sense? Okay. You have to make sure that you scale your axes appropriately. I saw so many people do this, and probably, you were moving fast, and there were lots of things like going on in your brain, and I get it, but this is one of those things that I just want to remind you of, that you want to make sure that you scale your axes from the smallest to the largest, but I would encourage you to scale it and then put data in, okay? So you can just do 100, 200, 300, etc., all the way out, and then put your data points in. Okay, so one thing you want to write down for example 1 is that we need to make sure to scale our axes correctly. Okay, the same amount of space for the same amount of mass in this case. Why? Because if you don't, then your slope is very different. Right? Because these should be stretched way over here to the right, which means that the slope would be affected quite a bit in that way. Yeah, that was the big thing that I noticed in this. Were there other things that people noticed in this graph that you'd like to talk about? I heard some other good conversation. Kaylee B, did I hear you guys having a conversation about the data points or something like that?
Oh yeah, we were talking about that. Like how they have circles around points that are already on the graph.
Gotcha.
And on the lab paper it said to use things that weren't already data points.
Sure. And I can totally see where you're going with that, because it looks like these circles here that they've right here, like this guy here and this one here, they do look very similar to where those data points are. I think in this case that the data point, like in this one here, was actually at 500 and then like 1 point something. And so in that case, it's okay. As long as the point that you're using for the slope is not the actual data point. Does that make sense? But you could totally have chosen a point like this one here that is completely separate, right? And that may be easier to find. Yeah. But that is a good call that you want to make sure that it's not your actual data points. Absolutely. Yeah. What else do you notice? Anything else that we want to add for this one before we move on? 2 good observations. All right. Here's graph number 2. Let's make it a little bit smaller so you can see it a little bit better. There you go. It's a really pretty graph. Whoa. All right. I'll give you just a couple moments to take a look. Write down what you notice. All right. For graph number 2. What's up, Ed?
Yeah, it goes off the pre-made graph.
It does. Did you guys see that? Mm-hmm. Yeah. So the graph is right here. And do you notice that there's a line here and a line here?
These are straight.
Yeah. Now, so here's the thing. Is that, and no disrespect to, like when you were in junior high science or whatever, like it looks pretty good. But friends, when you are trying to find a slope, it's really, really important that data points are plotted precisely, right? Because if the data is a little too high or a little too low or a little too far to the right or to the left, then your whole line gets messed up. So even though, these lines look pretty straight, but are we sure that they're perfect?
No.
And then there's another one, I just don't know. And if it's wrong, that's going to mess that up. So absolutely, we're going to write down, for example, number 2. One of the things that I noticed on this one was that thank you. Added data. You stop doing that, please. Thank you. I'll say added lines to the graph. Don't do it. Well, some will say do not add lines to the graph. Maybe that's a better way to say that. Yeah.
They put their dependent on the x-axis when it should be on the y.
Indeed they did. Yes. And again, not something that I saw just from one person. I saw this from a number of people. I drew a lot of little lines that looked like this. Yes, you got to flip them. The independent variable always goes on the X unless there's a reason not to, okay? So, for example, in AP Physics, sometimes we graph things in a specific way that make it so that the independent isn't here. But I will tell you, friends, that the only reason you would do that is because you have some physics that you're trying to show or that you know what to expect. In this case, we didn't. All we were trying to do was to figure out how does the mass affect the frictional force. That's all we know. So in that case, the independent needs to go on the x-axis and the dependent needs to go on the y-axis. True, true. Anything else that you notice on this graph? Those are the two big things that I had on that one. One more. Here it is. Take a look. Oop. I'll give you a minute to discuss. Write down what you see, then we'll talk. Kidding, not completely. All right, let's take a look. Ad, you got your hand up again. What you got?
Both of their lines start from the origin point, and in doing so, they leave out a lot of data points.
Indeed, they do. Yeah. These trend lines. Thank you. I appreciate you. Trend lines should not be forced through 0, 0 or the origin.
Where's the scribble?
She is out today. She'll be back tomorrow. So friends, I want to make sure that you're writing this stuff down, right? This is your opportunity to learn this, to have this written down. They've done studies. You know, if you write something down, it sticks in your brain way better than if you just hear it. So write it down so you don't forget. Trend lines should not be forced to go through the origin. I had a student, I don't remember if it was last time or when, but somebody was like, my trend line really does go through the origin. Is that bad? I'm like, no, it's fine if it legitimately does go through the origin. But in both of these cases, they probably don't go through the origin if you actually look at the data. I'm going to highlight here and take a look. I'm just looking at these ones here. So there, and there. If we take those data points and I take my meter stick and I try and do that, that's not really a super great, I think that one might be a little off and it might be like that. You know what I'm saying? Something like that. So you need to like adjust based on the data you have as opposed to just making it go through the origin. Okay? What you got?
It goes from the weight goes 200 grams, 500 grams, and 700 grams.
It does the same thing, doesn't it? Yes. Scale your axes. I put it in there twice, well, partly because I like this graph too, but also because, yes, got to not forget that, right? Okay? Scale the axes appropriately. Oops, except I can't spell. I can scale, but I can't spell it. Scale axes correctly. Please and thank you. Absolutely. Anything else you notice? What else do you see?
They have some blank space at the top, so they could probably scale their force with more decimal points.
They probably could. Yeah, they probably could have done that. I will tell you that if you use at least about 2/3 of your space, I'm not going to get too bent out of shape about it. Like if you just graph in this space right here, that's pretty yucky, right? But if you use at least 2/3 of it, then I'm going to be okay with that. Because sometimes the scaling is really tricky, and I don't want you to have to like do yucky division. Do you know what I mean? But at the same time, using most of the spaces is best. Yeah. Anything else you notice? There's one more glaring error, and then there's one little thing that I noticed as well.
Weight, not mass. Oh.
Yeah. Are weight and mass the same thing, friends? They are not. Mass is measured in grams, kilograms, whatever. And you could have written it down in grams or kilograms. It doesn't matter, right? In physics, we use kilograms as the base unit. Dawson, it's fine. You don't need, turn around. Please turn around. Thank you. But I don't care if it was grams because things were measured in grams. But grams is not a measure of weight. It's a measure of mass. That is 100% true. That should say mass. Okay? Weight is measured in what?
Just kidding, ounces.
What units do we use in physics to measure weight?
Pounds.
Somebody said it over there. Newtons. Newtons.
That's force.
That is force, right? Weight is a force. It's the force of what?
Light.
Say it loud. Gravity. Yeah, friends. We went through this last week, and I need for you to know it. So if that didn't pop right into your brain really fast, then make sure you're paying attention. Weight is a force. It is the force of gravity, the force of the earth pulling down on you. In the imperial system, we use pounds. But the imperial system, we also measure length in inches. We don't measure length in inches in physics or in any science or pretty much in anywhere else in the world except England, right? Same. We're going to measure weight in newtons, right? That's a force, okay? The last thing is kind of a little thing, and I had better examples, but I didn't want to throw so many examples at you because we have other things we need to do. These ones were kind of easy to tell, but they were a little bit difficult because the black and blue are very similar in color, and it's kind of hard to tell what's going on with the data if they're all just little dots with colors that are really similar. So just a note that it's helpful if you maybe mark one of them with like little X's so that I can see where those other, so you can kind of differentiate between the two. Okay? Questions that you have for me? Yeah.
Will we get points taken off if the colors are too like
No, I didn't take points off for that, but I just was like, oh, this looks kind of, yeah, but no, that's fine. All right, so what I'm going to do right now, I am going to hand your labs back. I also am going to hand back the gold sheets or these little half sheets. If you put your name on it, if you didn't put your name on one, then just come up and get one. I'm going to give you about 3 minutes to work on this lab and the lab analysis. Now, let me say really quickly that some of you were not here to do this lab. If that includes you, okay, what I'm going to ask is that you talk to your table partner and answer the questions from the sheet go ahead and answer those questions based on your table partner's data. We will make arrangements for you to come in and actually finish the lab and do the rest of the analysis, but not today, okay? All right, I'm going to give you about 4 minutes or so to work on that, and then we are going to get started. So if you know you didn't put your name on stuff, go ahead and get some for now, and then we will regroup. Talk, shall we? Okay, so as I said to some people, but maybe not everybody heard me, and that's totally fine. You are not going to turn this sheet in. This is just an opportunity for us to kind of collect our thoughts so that we can have a common discussion. Thank you. So I don't need to fill this in. The thing that I'm hoping that you saw based on your data is what? Which type of friction resulted in a larger slope? It should not matter whose data we're looking at. For everybody, we should see. So I want everybody to answer the question, which type of friction has a larger slope?
Kinetic. I'm kidding. Static.
Static, right? He's so funny. What a joker.
I thought it was funny.
The answer should be static. Hopefully that's what you saw. On some of your graphs, I wrote a couple of things. One was like, oh, maybe there's some outliers because what I saw was that your kinetic slope was larger, which is not what it should be, right? The static slope should be bigger. We're going to talk about why that's true in just a minute. But first, I want to move on to question 2. Question 2 says, based on your lab analysis, answer these questions. And what does it say? Provide evidence. That's the key. Friends, I didn't ask you to write a conclusion for this lab, but I will again soon. And basically, this is what I'm asking you to do. Question A here is really just the first half of the research question. How does an object's mass affect the static frictional force? What was your answer? How does the mass affect the static frictional force? I'll give you the first half of the answer. As the mass increases, what? Static friction increases. Yeah. And if you were writing this as part of a conclusion, then you also need to provide evidence. So let's do that. What would that look like?
Slope.
It's not the slope. That's the piece. That, well, I mean, I guess, tell me what you mean. I shouldn't cut you off and say no.
Well, I was more thinking like if we're comparing static and kinetic.
Yeah, but I don't want to yet, right? That's why I'm kind of teasing this apart. How does the mass affect the static friction? As mass increases, static friction increases. What evidence do you have for that claim? Yeah.
Points that you have in math.
Yeah, so you could say something like, for example, at 200 grams, I have a frictional force of whatever, right? And at 700 grams, I have a frictional force of whatever. And this one's bigger than that one. Absolutely. Now, Ryan, I feel bad because I cut you off when you said slope.
Yeah.
Because I thought you were going kind of the place you were going, but you could use slope as an answer here. Friends, I feel like there's a lot of people that are not with me. I need you with me. This is stuff that's important and I want to make sure you get it. How could you use the slope of the mass versus just the static frictional force to answer this question?
It's a positive slope.
Has a positive slope, right? A positive slope indicates that as one goes up, the other goes up. So you can absolutely do that too. You could say that the graph has a positive slope, indicating that as one increases, the other increases. That's 100% fine. Yeah. 2B. How does an object's mass affect the kinetic frictional force acting? Is it very different from part A? It's not, right? Because just as the static frictional force increases, so does the kinetic frictional force, right? So we'd say as mass increases, static frictional force, or excuse me, kinetic frictional force also increases. Getting a little lazy there. Provide evidence, same process, right? You can either say at 200 grams this is bigger or is smaller than at 700 grams, or the graph has a positive slope, which means that as one goes up, the other is going up as well. Part C. For any given mass, how does the kinetic friction compare to the static friction? Did you have a chance to talk about this one at your tables or no? Do you need 30 seconds? 15 seconds? Go. Do it right now. Answer that question right now. It should be loud physics right now. Go. I know, that's what I'm asking. To be part of the conversation. For any given mass, how does the kinetic friction force compare to the static friction force? It's less. Indeed it is. The force of kinetic friction is always less than the force of static friction. You knew this without having to do all the other analysis and stuff because, friends, you did this before. This is when you had the time and the forces is what you saw on your computer. It goes zoop, right? Every time the static is bigger than the kinetic. Every time it is. Yeah. This is why when you try and move that couch or that really big box or whatever, it's really hard to get it started. But then as soon as you get it moving, it's much easier to move. Right? Yeah. The kinetic friction is always less than the static friction. And that also relates a little bit to question 1, which was which type of friction is at larger slope? Not only is it larger, but it gets bigger faster. Okay? This is due to, and this is just a little thing that I want to throw out there because I can't not tell you, okay? This is due to this thing that we call the coefficient of friction. The coefficient of friction is a number that describes how sticky or slippery two surfaces are moving relative to one another. Okay? Think of yourself with your shoes walking on grass versus walking on ice. In which case do you have less friction? Ice, right? Because there is a lower coefficient of friction. Okay? The coefficient of friction is marked on the graph essentially by the slope. Okay? So not only is the coefficient of friction dependent on the materials, but it's also dependent on whether it's not moving or is moving. Okay? So that's just one of those things that, especially if you go on and take another physics course, regardless of where you take it, they're going to start throwing this at you and expecting that you've heard it. So at least you've heard the word once. Okay? Questions about this lab for me before we move on? You can hold on to the lab. That is yours to keep if you have not yet finished it. As we start this, the next thing that we're going to do, I'll come around and find out when you're going to do the lab yourselves. We are going to start some ranking tasks right now. We've got a little bit of time, and we're going to do some ranking tasks. I mentioned to you that on Friday on your test, there were going to be some problems, but there will also be some things that look like this. Friends, you have been well trained, or should have been well trained by now, or you're moving in that way to solve problems using this big chart. And I like that, and I want you to understand how to do things, especially the hard problems this way. But not all Newton's laws problems are going to look like this. Okay? So today we're breaking out of the box. We're starting to think about physics without putting it in a chart like this. Okay? That's what the intention of this is. So here comes the first one. You guys remember these ranking tasks? It's been a little while since we've done them, so welcome back to them. I'll read this to you. In your notes. Get out some paper to write.
Is this a warm-up kind of note?
I would just say some notes. It's not a warm-up problem. I've got 4 of these to work on today. Here we go. Various similar boxes are being pushed 10 meters across a floor by a net horizontal force as shown. The mass of the boxes and the net horizontal force for each case are given. All the boxes have the same initial velocity of 10 meters per second to the right. What I'm going to ask for you to do here before you jump in and have a conversation, I'm going to ask for 30 seconds of your brain, 30 seconds of physics in your head. Write things down, write ideas down, because on Wednesday and on Friday, you won't have everybody right next to you to talk to. So I want you to try that first, and then I'll let you talk. Okay? Engage with this right now. You and your brain. Make it happen, friends. I'll let you know when it's okay to talk. So right now you're not talking. Right now you put those boards up so I can see them. I can't see it when you move it like that, so super. There's no E, yo. A, D, C, B. Did I see yours, Ava? Did you guys put yours up? I just want to make sure it matches. A, D, C, B. All right. This is what I'm seeing. Okay, that one's different.
No, it's not.
Talk to me. Now,
No, it's
oh, so okay, yeah.
Everything is there.
So there's a little bit of dissension in the end. At the beginning, it looks like we've all got the same answer. How do we approach this question? What did you do first? How did you figure it out?
F net equation.
F net equation, what do you mean?
F net equals M.
It is. I like to write it this way best myself. And in fact, that's really the best, yeah, in this case. But yes, F net does equal MA. Solve for A, okay? So we just take the force divided by the mass. The bigger the force, the bigger the acceleration, the smaller the mass, the bigger the acceleration. Let's double check B and C. Can we do that? Because I've got some BC and then I got some CB. Which one's the right one? Prove it to me. Figure it out. Andre, what did you say?
C.
You think C is bigger? How do you know? Can you do the math for me? So C is going to be 75 divided by 20. Is that right? Which is what?
It's like 3 and 4/4.
3 and something? And then tell me about B.
It's 3.25.
B is 3.25?
Oh no, it's 3.3.
Okay. Which one's bigger? C? How are we doing, team? We okay? All right, let's do another one. Again, friends, this is all physics that you know. It just looks a little different. But apply the same principles that you had before. I'm going to read it to you, then I'll give you 1 minute to think by yourself, and then I'm going to let you discuss. All right, so here we go. The 2 blocks are attached by a rope to a wall. A child pulls horizontally on a second rope attached to each block. The blocks remain at rest on the frictionless surface. The weights of the blocks and the magnitudes of the forces exerted by the child are given. It says rank the tensions in the ropes. So I'm going to give you just a moment to think about this by yourself, so it should be quiet, physics time, and then I'll give you time to discuss, okay? So engage with this problem. You can do it. You have enough physics to do this, but it needs to be quiet. Okay? It needs to be quiet, please.